This lecture is about ROC curves, or receiver operating characteristic curves. These are a very commonly used technique to measure the quality or the goodness of a prediction algorithm. So in binary classification, you're usually predicting one of two categories. So again, you might be predicting whether someone's alive or dead or sick or healthy. You might also be predicting whether they'll click on an ad or whether they won't click on that ad. But your predictions often come out to be quantitative. In other words, almost all the modeling algorithms that we have won't just assign you to one class or the other. They might give you, say, a probability of being alive or a prediction on a scale from 1 to 10 about whether you'll click on the ad or not. The cutoff you choose gives different results. In other words, if we predict a probability that you're going to be alive is 0.7, and we say all the people above 0.5 will be assigned to be alive, then that's one prediction algorithm. Alternatively, if you say only people with a probability above 0.8 will be predicted to be alive, then that will give you a different prediction for that same person. And the different cutoffs will have different properties. They'll either be better at finding people that are alive or better at finding people that are dead. So what people use is what's called an ROC curve. And so the idea is on the y-axis, what they usually plot is 1 minus the specificity, in other words, the probability of being a false positive. And on the y-axis, they plot the sensitivity or the probability of being a true positive. And so what they're trying to do then is make a curve where every single point along this curve corresponds to exactly one cutoff. So for a particular cutoff, you get a certain probability of being a false positive or a certain specificity, and that's this point. 1 minus the specificity is this point right here on the x-axis. At the same time, you get a certain sensitivity, and that's this point here on the y-axis. And so you can use these ROC curves to define whether an algorithm is good or bad by plotting a different point for every single cutoff that you might choose, and then plotting a curve through those points. So this is an example of a couple of algorithms that are used to predict. So these are examples of what real ROC curves look like. So for example, if you want to look at, say, the NetChop algorithm, and you look at, say, 1 minus the specificity is equal to 0.2, in other words, the specificity is quite high, it's 0.8, you can trace that number up, and you get about here on the curve, the red curve in this case, and that corresponds to a sensitivity of only about 0.4. So it's very highly specific, but not very sensitive. And similarly, if you move out here to the right on the x-axis, you'll get less and less specificity and more sensitivity. And so this curve tells you a little bit about the trade-offs. Now, although the curve tells you a little bit about the trade-offs, you may actually want to know which of these prediction algorithms is better. And one way that people use to quantify one curve versus the other is they basically calculate the area under the curve. In other words, they follow, say, the red curve here, and they trace the entire area underneath that curve. So that'd be this area down here. And so that area quantifies how good that particular prediction algorithm is. So the higher the area, the better the predictor is. And so there are some standard values that make sense to pay attention to. So if the area under the curve, or AUC, is equal to 0.5, that's equivalent to a prediction algorithm that's just on the 45-degree line. And that's equivalent to basically randomly guessing whether you're going to be a true positive or a false positive. So 0.5 is actually quite bad. Anything less than 0.5 is actually worse than random guessing, so it's worse than flipping a coin. AUC of 1 is a perfect classifier. In other words, you get perfect sensitivity and specificity for a certain value of the prediction algorithm, and so that's the perfect classifier. In general, it depends on the field and it depends on the problem you're looking at, but people often think of an AUC above 0.8 to be considered to be something that's sort of a good AUC of a particular prediction algorithm. In general, something to pay attention to is how did you just look at an ROC curve and decide whether it's a good ROC curve or a bad ROC curve. So remember, the 45-degree line corresponds to just guessing. In other words, the sensitivity and the specificity match each other on this particular line. So a perfect classifier goes at 1 minus the specificity. So 1 minus the specificity of 0 means perfect specificity, and it jumps straight away up to perfect sensitivity, and then straight over. So that curve represents a perfect classifier when it goes straight up to this corner. So the farther you are towards the upper left-hand corner of the plot, the better the ROC is. And the farther you are down to this bottom right-hand corner of the plot, the worse the ROC is. And so points along or graphs along the 45-degree line or below are considered pretty bad, and you want your curve to go as straight up towards this top left-hand corner and over as much as you possibly can. So that's how you interpret an ROC curve, which will be used later when we're picking out particular values of predictors of binary outputs that output quantitative numbers.